When engineers require a large language model to produce a strictly factual output, standard practice dictates locating the temperature parameter and dropping it to 0. Engineers often treat this single hyperparameter as the primary mechanism for toggling between creative exploration and absolute precision. Yet a model outputting the exact same sequence of tokens every time it executes a prompt does not mean the output is factually correct. Artificially forcing consistency through parameter truncation fails to engineer true structural reliability. To understand how a neural network actually achieves precision, we must look past standard coding paradigms and map the architecture back to the physics it borrows its terminology from, statistical mechanics. Systemic precision is not generated by a mathematical scaling function. It is driven entirely by dynamic constraints applied at runtime. Resolving this paradox requires analyzing how two distinct forces operate: the physical microstate of a thermodynamic system and the informational microstate of a language model. By treating a simple mathematical division step as if it physically freezes a system into a solid state, developers place a hard mathematical limit on the actual reliability they can achieve. In 1948, Claude Shannon published the mathematical framework that bridges physical thermodynamics and modern information theory. He utilized the concept of entropy. In both fields, entropy is a rigorous mathematical measure of uncertainty within a probability distribution, dispelling the colloquial definition of mere disorder. In this model, microstates are discrete atomic arrangements defined by spatial coordinates and velocity vectors. High entropy occurs when probability mass evenly distributes. Mapped onto a language model, these microstates become a high-dimensional manifold of token sequences, generating a continuous probability curve across the space. Under the Shannon formulation, the underlying mathematics dictating these two spaces behave identically. When the probability mass spikes into a concentrated area, entropy drops, indicating high certainty. Conversely, when that probability mass is dispersed widely across the manifold, entropy rises, indicating high uncertainty. Whether the system contains colliding gas particles or predictive linguistic tokens, system uncertainty is universally quantified by exactly how thinly its probability mass is stretched. Both disciplines use the exact same variable to influence this entropy, temperature, denoted as T, yet they represent completely divergent operational mechanisms. In physics, temperature is an ensemble average of kinetic energy. It measures the physical speed and violent collision rates of particles within a closed system. An artificial neural network operates in a digital vacuum. It contains zero physical kinetic states, mass, or thermal energy. This visual shows the equation governing LLM temperature. It is strictly a sampling hyperparameter used to divide the model's logits. Logits are the raw, unnormalized scores a neural network assigns to every possible next token before converting them into probabilities. When a developer increases the t-value, it raises the denominator in the equation. This mathematical division artificially flattens the probability curve out, pushing the entire distribution toward higher entropy. Bringing the mathematical scores of all potential tokens closer together enables stochastic exploration, allowing the system to sample lower probability token sequences. Driving the t-value down toward 0 performs the exact inverse operation. The division causes the flat probability curve to sharpen drastically, mathematically isolating only the highest probability tokens. This operation mimics structural order by violently concentrating the probability mass into a single point. By eliminating stochastic exploration, the system strictly enforces output consistency. However, this division equation does not add a single piece of new factual knowledge to the model. Adjusting LLM temperature manipulates a math equation to fake certainty. It scales the numbers, but it does nothing to alter the system's foundational understanding of the prompt. The distinction between physical reality and logit scaling exposes a divergence in their structural limits. Thermodynamic systems are bound by fixed, inescapable constraints, such as a static container volume and a conserved total energy output. Bound by these static physical laws, these systems inevitably evolve toward maximum entropy over time. Language models do not possess static containers. They operate entirely under dynamic constraints generated the exact moment the model executes a runtime sequence. The input context, the text prompt, acts as the primary mechanism for establishing these dynamic boundaries. This curve represents an uncertain state. Lowering temperature slices away the outer tails. The center peak remains unmoved. In contrast, a structured context prompt introduces a hard constraint, physically shifting and compressing the distribution laterally, forcing a spike into a new targeted location. This context injection reshapes the probability space itself, structurally forcing the system into a genuine state of lower entropy. True reliability is not achieved by silencing the mathematical noise with a temperature variable. It is achieved by physically moving the probability mass to the correct coordinate through structured context. Returning to the initial paradox, dropping the temperature to 0 only guarantees that the model will confidently repeat the exact same output. It offers 0 guarantees regarding factual accuracy. Absolute systemic reliability demands that the input context be flawlessly defined, eliminating all stochastic variables before the computation even begins. A mathematically rigid context removes the need for the model to guess. It cleanly shifts the underlying mechanics away from stochastic exploration. This highly controlled end state is defined as architectural precision. Reliable language modeling requires practitioners to design the specific geometry of the container the probability mass inhabits. This structural change accomplishes what temperature reduction only attempts to simulate. Temperature merely scales the mathematics. Context alters the actual physics of the model state space. Practitioners seeking precision must transition from scaling mathematical outputs to designing the structural constraints of the state space itself.